Hey everybody. So we're back here with some differential dataflow programming. And what I'm going to try to do over maybe the course of a few videos now is build out something that I'm hoping is going to be pretty cool. Well, at least I'm going to enjoy it. So my plan is to try to build up an implementation of Minesweeper, the sort of the classic Windows time-killing game, but do it in differential dataflow. And we'll as we go along, we'll try to explain why that might be interesting, or why this fancy data parallel thing for Minesweeper, and scale is going to be the main reason. Scale, and also just to learn a bit about programming and differential dataflow again. So I thought I'd start just with a little bit of design work to try to explain what I'm thinking and what we're going to do in the context of Minesweeper. So if we look over here. If you're not familiar with Minesweeper, or even if you are, and we're going to just get some common context, Minesweeper is this game that's played on a relatively large grid, and in each of the locations, there sort of may or may not be a mine. And what's dangerous about the mines is if you click on them, the game ends, you lose. And the only way you have around in the game is that when you do click on certain regions, it'll tell you the number of mines immediately adjacent to that square, or in the 8 cells around that. So we might see the number 3, for example, and that will tell us that 3 of these 8 surrounding squares have a mine in them. And you're meant to use certain amounts of reasoning and cleverness to try to figure out exactly what's going on. And in so doing, basically what you're going to do is make a bunch of guesses at particular locations, and our job is going to be to reveal to you, you guess somewhere else, maybe there's a 2 here, reveal to you the number of mines adjacent to your guesses. So we're going to have a few goals. One goal, reveal the counts. So this is not necessarily super complicated algorithms. It's just sort of counting of things immediately adjacent to some cell, but we're going to do it anyhow. There's another thing, though, that Minesweeper does, which is pleasant, sort of ergonomic, which is that if you click on something that has no mines around it, like let's say that region has no mines, basically if you get a 0, if you click on a thing and the count is 0, that essentially tells you, tells all of us that everything around that square is safe to click on. So each of these cells here around the 0 are safe to click on. So might as well just go and do that, right? Don't make the human actually go and do that. We're going to automatically, essentially, click for you all of those locations. So this is a second goal that we're going to have here, is to sort of unfold empty regions. And this is maybe a bit more interesting now, because this unfolding is something that happens iteratively, right? Like if this square here is also 0, we're going to want to keep going and sort of spill through out these empty regions. And I don't know if you're like me at all, but in playing Minesweeper, this is a very satisfying moment when you unfurled a large empty region and just large chunks of the map opened up in that case. And it sort of continues off until you start to see numbers around the periphery. Perhaps I guess we can't have those there because that's also 0, but essentially this will spill out, and that's plenty interesting, exciting, and an important part of a good Minesweeper implementation. Plus, it will tell us, it'll get us to use iterative computations in differential dataflow. And there's a third thing we might do as a stretch goal. We'll see how it goes. Which is that in the normal Minesweeper, you're allowed to place little marks. Basically, you're allowed to flag a thing as a little mine. That looks like a 1. That's not what I want. I forget what it looked like in Minesweeper, actually. Let's just do a little flag, though. And what the flag does is it sort of notes to yourself about where there might be mines. And it'd be neat, we could let people flag locations. But this could totally tie back into the unfolding. So as soon as you've flagged enough locations, basically, flagging a location, we could think of that as dropping the count in each of the adjacent regions by 1. That's sort of, if we think of the count as the number of unaccounted for mines, Then flagging a location drops the counts around it by 1, and if anything hits 0, great, just sort of go and unfold all of those regions as well. And this is, just a little bit of sort of helpful UI type of thing. Yeah, we could imagine some more things we'll have to get into, like, do we want to actually start writing a solver for this, right? If there's a region that says it's got k mines around it and there's only k spaces, maybe we should go and unfold that. That's usually often pretty common, right? You'll get like a one of these little corners where maybe there's who knows what around here, but you end up with the number. Keep going off this handy green here. You end up with the number 1 in the corner here. That's a 1. And so there has to be a mine right here, and we could totally figure that out all on our own because there's only one empty space, one unaccounted for space around the 1, and dropping that flag in. This is just again more iteration that we could be doing, but doubly nested iteration in this case, sort of solve, unfold, and repeat. All right, now this is all potentially interesting, or not. We'll see what you think, but. What I'm also totally interested in doing at the same time is building a Minesweeper solver that is not limited in its size. So often, when you're playing Minesweeper, you pick a size and some number of mines you want to drop down into it. And I propose that we do things a different way, which is to have essentially an unbounded Minesweeper terrain in front of us. And I'm not sure what to call this. This isn't going to be after 4, so we'll call this A. So we're going to do mines not based on sprinkling a fixed number around, but mines based on density. So we could say, for example, 1 out of every 10 locations might be a mine, and you sort of think about how you might do this by hashing up the pair xy, and then comparing it to any fixed value mod 10. This is a sort of cute way to allow us to have a potentially unboundedly large playing area, just bounded by whatever these types are. If these are going to be U64s or something like that, okay, it's going to only be so large, but we can totally get you started playing anywhere and just have the map go off indefinitely in every direction. That's going to take a little bit of care because obviously, we're going to want to set up our computation so that we don't drop mines explicitly anywhere in the graph. We only discover or even explore where mines might happen to be as people start asking questions. And I want to do this mostly because there's a really cool webpage that I bumped into a few months ago. I'll try to find a link and put it in the description, that had essentially a big cooperative Minesweeper going on, so that lots of people could log in and go into different parts of the graph. There's a little mini map that sort of shows you what was up, and as people claimed different regions as safe, they got to put their little logo on it. Stuff like that. It just seems sort of cool, and I was sort of imagining that you can get like a nice large scale Minesweeper implementation that presumably only I would ever play, but it would still be cool to sort of exercise that and see what would happen if, in principle, you might point 100 or 1,000 people at this, adding and removing guesses at various concurrently, but then attempting to maintain this sort of consistent computation across all of it. So that's the plan. Sort of leave these notes over here, but I was going to look over at my laptop now and get typing. So what we have here is a new little project that I've created. You can sort of see there's a few things here. We have cursive, which is something that I'm playing around with. I'm trying to learn a bit about the right way to present information visually without requiring too much heavyweight nonsense, and cursive seems pretty cute so far. We'll grab timely and differential, just whatever versions happen to be out there. We're not going to use any fancy features of them, I don't believe. And we've got here just the shell of a program that we're going to start typing into. So I'm just going to write some boilerplate first. So we always start our programs typically with spinning up a timely data flow computation. Use execute from args for this myself, which allows to take the standard environment arg, whatever args come in from that are supplied with the program. This allows us, if we want to easily write a program that sort of scales out to multiple worker threads or across multiple worker processes if we want. And we're going to write a closure that is going to tell each worker what to do, and so that we don't get our little Rust plugin here massively frustrated at us. We're going to make sure that some properties hold, like that we use the results. And just put some comments in here. So what we're doing in this closure, if you're not familiar with timely data flow, is explaining to each of the worker threads what they should be doing. And generally speaking, they should all be doing the same thing, which is to build up a data flow computation and put some data in it and start collaboratively working on that. But this is the idiom here, so we're going to write what appears to be sort of a single-threaded hunk of code inside this closure that spins up on multiple workers, and some communication fabric behind the scenes makes sure that work balances across each of them. So what I typically do here, when I'm not entirely sure what I'm meant to be doing next, is write some comments describing what I intend the computation to look like, what are its inputs, what are its outputs. So I thought let's just start with some inputs. So I think we're going to probably have as inputs a collection of guesses. Say like U64, U64. And what these guesses are, they're not guesses where there are mines, I should say, sorry. These are probes, let's call them. These are places that you've actually gone and sort of poked in your Minesweeper grid with the idea that you'd see if there's a mine there or not. And if there is, too bad, and if there isn't, you get told a number as a result. So our output is meant to be a collection of counts, I suppose. All right, so these are going to be the counts at various locations. And let's say it's a U64 or U64, so a location followed by a count, which we can make be a U8. I guess it doesn't have to be particularly tidy, but we know that it's never going to get above 8. That would be really lucky if it was, because it means we just narrowly missed a catastrophe. So what does this look like? Let's build up a new input collection. So the way we do this in differential data flow is we first go and essentially create some new inputs. Let's see if I can remember how to do this exactly. So we're going to have two things, a handle and an input. Typically what I do, by the way, is 100% copy paste from an existing program. I'm trying not to do that now because I was asked, could we walk through this in slow detail so that other people who aren't quite as comfortable just copying and pasting new things can get the same vibe out of this. So let's see. Let's do. I think it's dataflow input handle. Yeah, great. We're going to make two things: an input and a probe. This probe is unrelated to the Minesweeper probes. I have no idea what these complaints are. We'll eventually get to compiling them and seeing what's going on. So the input is going to hold on to our input probes. I need a better term for that, but the Minesweeper board. And the probe return, this is a timely data flow term. The probe that is going to come out the other side will tell us about progress through the computation. So it's what tells us, are we done with a particular round of input or not? So what we're going to want to do now is this worker, which I suppose we can get rid of the underscore now. I swear this Rust helpful thing that tells us that yes, our entire program is malformed at the moment is driving me wild, and we might have to change it. So we're going to build a data flow. What is the data flow? You take it has 3 generic arguments, which are going to be there's a timestamp type. So the data flow has, all data flows have some timestamp that advances through the data flow. Sort of as inputs advance, what thing gets incremented. And it's got a return type and a closure type. And we're not going to worry too much about those things just because they're a little hard to specify exactly. And this is where we describe our computation. So we've set up sort of the input and output, if you will. And now we just want to describe how does the computation unfold. So scope dot, oh my word. I'm hoping that it's, oh, this is super exciting. I mean, the plus side, I suppose, of having these Rust autocomplete things is that they can tell you what's going on here. There's a timely trait that allows us to introduce an input handle into a scope. I'm struggling to remember exactly what it is. Let's just write this for the moment. So roughly what's going on here is that input is a thing that needs to exist both in our computation as a stream of data that we can manipulate declaratively, essentially. When the data actually show up, we're not actually peeling records off of them ourselves. But outside the data flow, we're going to need something that we can actually imperatively jam some data into to get the computation going. Fascinating. We'll debug this in just a moment. I sort of want to try to get the structure down first. So the stream is going to have some type. We'll get to what that type is in just a moment. It's going to be an appropriate type for differential data flow. So we're going to take our stream and call as collection on it. This is an important differential data flow method that is what takes just a random stream of data into, which is, who knows what, just random records, but into something a bit more semantically meaningful. In particular, it's going to be changes to an underlying collection. And it's important to take the stream, turn it into one of those, and that opens up a whole bunch of fun differential data flow methods. So I'm going to go back to calling these things guesses, just so that we can not have to use the word probe over and over again. And I'm just going to, that was perhaps overwrought formatting there, but that's okay. So what do we do with our guesses? Our guesses are meant to be a collection of XY pairs, right? And our goal is to try to produce for each of these XY pairs a count of the number of things immediately adjacent to it, number of mines immediately adjacent to it. So one thing that we can do, if we want, is go and essentially create each of the 8 locations that are adjacent to a particular XY pair by adding and subtracting 1 or not from each of the coordinates. Figure out if there's a mine there, and if so, sort of essentially send a number back. So let's do that. Let's take our stream of guesses, and we do a flat map. And I say flat map because for each individual record here, we're thinking about, I'm thinking about at least about probably producing up to 8 output records, depending on what's going on there. We have an XY pair coming in here, and we could do this cleverly with iterators and such. I'm thinking for the moment, I'm just going to use some imperative programming. So let's do let mute results equals vec new. We're just going to stash some results in the vec and then return results at the end. But in between, let's do blows my mind that I don't know a brilliant way to write this. So we're going to walk through each of the possible changes we might make here, and what we've got now is let xp equals yp, p for prime, I suppose, plus j. We'd like to now think about whether there is a mine there. Think about if there is, then we should stash some number back in into results. And if there's not, well, we just, no particular information here. Now, we haven't actually talked about how we're going to figure out whether there's a mine in a location or not. And I was thinking that we might do something like dot hash. There isn't a handy hash method the same, like C# has one of these everywhere, and it's super nice. There is a dot hashed method that I wrote for, you have to like pull it out of differential dataflow, and it's just a thing that can be hashed. And what we're going to do, I'm just going to do something fairly simple. We'll bake this in for the moment. But more generally, we could come in with a either a closure, some explicit predicate, or just two numbers here that we might use that are fractions describing what fraction of cells should be a. Actually, let's do that right now. So I suppose it should be strictly less than, probably. So if we have a numerator and denominator, these two are going to, density of mine density will be numerator over denominator. Yeah. And we're not going to explicitly write down how many of these mines are. We're just going to take a hash of a thing and say, you know what, if when we take your hash value and it's whatever it is, modulate it up by the denominator and compare that to the numerators to give us roughly numerator over denominator fraction of mines flopping out all over the place. Now, if this is the case, then we're going to want to push into results another copy of x, y. And in fact, what we're doing now that I think about it, we're not even really doing a flat map in some sense. We're taking each of these x, y's, and we're looking at all the neighbors, trying to come up with a count, right? And there's a handy function for doing this in differential dataflow called explode, which it doesn't. It's a way to produce a variable number of counts of a thing. So it's a way of taking individual records and producing things that might have multiplicities without actually having to form all of the multiplicities. So what we're going to do instead is actually just get a sum. We're going to count up the number of times we want to see a particular thing here. And instead of pushing in x, y here, we're just going to do sum plus equals 1. And now at the end, what we're going to return is a pair of x, y, and whatever the count tended to be. So explode is meant to return an iterator, and the things that the iterator contains are pairs, an into iterator. Option is an into iterator. And the things in the iterator are pairs of data and counts. So this will return as many copies of x, y as sum added up to. So we should call this neighbors. These are the number of mines that are neighbors here. And for the moment, let's just check out these results. So let's do a little inspecty over here, which is something, it's a handy little differential dataflow method that will let you run essentially any little bit of code on a diff that flies by. And we'll just print out the results there. Actually, before we get too proud of ourselves, let's put a probe width at the end. Yeah, and the only problem is that input from doesn't actually exist. So let's see if I can remember what the I'll hop over to the timely repo and see if I can remember what that input trait is. So the input trait, great, has an input from method. That's what we wanted. And I think we might just need to use that doesn't seem happy, but why is that? It's in operators? Yeah, it's in operators. All right. And okay, now we've moved on here. We need a few more things. So we'll use differential dataflow as collection. And all right, we can't do this quite yet because we're still a little confused as to what the type of stream is. So so the way that works is that somewhere along the lines, Rust is unable to infer the type of input because we haven't actually used it yet. All right, so let's do something like input dot insert 0, 0. Method insert found. I don't believe you at all. Why is that? Oh, I think yeah, this is there's a different input handle from differential dataflow. So let's take a little peek here at what the input handle here supports. It's got some nice low level-ish stuff. Actually, no. We want the differential dataflow one. It has a few other important methods that will make our lives a lot easier. So there's this other handy new input thing. This thing called an input session here, which is actually going to be what we want. And what's the best way to construct this sort of thing? We can do a new collection on a scope. So let's just do that instead. So rather than having an input handle, that's too bad. This input. Which differential dataflow? Yeah, it just lives right there. What am I missing? No, we'll figure it out, I suppose. So we will not use these traits anymore. We won't need as collection anymore. So let's cargo check what's going on over here and get some more explicit. All right, so this is good. The explode method apparently does not exist. Let's go and find. It's on collection. Why does it not appear to exist? This is classic. This is like the Rust debugging process is largely like. No, wait, hold on. Sorry, our program is just massively wrong at the moment. Anyhow, let mute input equals. So because we didn't create an input outside and then use it, we need to actually go and return our thingy in collection because I've forgotten. Returns two things. It returns the session, input session, and the collection itself. And we'll want to return input at the end down here. So what we've done now is we've created a pair up here of input handle thing that we can imperatively drive around, and guesses, which is a slightly more declarative stream E thing that we're describing what we should do, but haven't quite gotten to actually manipulate yet. And at the end, we need to hand the imperative thing back out of the data flow so that we can use it. And Rust is now angry with us that we're trying to have negative ones up there. For some is not live long enough. Okay, that makes sense. Then move and move. Great. So that apparently apparently compiled. Let's see what happens if we run it. Sorry, compiled it. It passed cargo check. Fascinating. So what did we observe? We observed 0, 0. Sorry, a whole bunch of zeros. Let's try to read out what this thing actually says. What it's telling us is that we observed a diff of 0 at time 0 for location 0, 0, which is a bit silly because normally you don't see diffs of 0 anywhere. And apparently what this is telling us is that there are no mines around this particular thing. But I was hoping a different thing would happen. We get to show off something. So let me fix this briefly. I'll just put a consolidate in here, and we might need to use consolidate. And I was going to make a cunning point. Oh shit, we still see it. Wait, hold on. I'm mystified now, actually. Like a differential dataflow is supposed to like throw this junk away and not actually show it to you. Let me throw in some stuff here. The thing I was hoping to show off was that if the count comes back as if there are no neighbor mines, we shouldn't actually see a record at all. Like this shouldn't ever print. It is printing though, and that's winding me up. So let's see. I'm just gonna put in a little print line here to see what we're actually computing as our sum. Yeah, so the sum is 0. For some reason, consolidation is not actually dropping on the floor. So I'm very surprised that we're actually seeing a thing here. And as I say, this is not how this is all meant to work. Well, I'm gonna try to figure out what's going on, or I can try to just like ignore it for the moment. Let's ignore it for the moment, and we'll sort of keep our eyes on it. And there'll probably be a good explanation later on. All these operators are sort of, especially consolidate, is meant to say like, if you give me a thing, and it adds up to 0, I'm gonna drop it. Actually, let's look at the implementation of this thing because it's really not that complicated. Well, I say that, but yeah, so consolidate just calls into consolidate named, and what it does is it creates a differential dataflow arrangement, and slams all this data in there, slams some zeros basically in there, and we really expect not to see a thing there. Let's do another thing. Now I have to put some more operators up here. The count operator will take each of the numbers that we've produced and put a number next to it. So this is telling us, this is fascinating. There's actually this is super embarrassing. It's like, as far as I can tell, there's a bug here. This is telling us that the triple 0, 0 with a count of 0 occurs at time 0 and has 1 occurrence. So we actually see 1 instance of this record. I very much don't want this record to exist, though, so I'm going to off camera go and make sure that doesn't happen anymore. Let's tweak this a little bit and see if we can produce a few more mines nearby. Great. So here's a different, with a sort of more aggressive mining of the area, I suppose. We can drive the count up. We see 5 nearby mines, and the number 5 showing up next to our 0, 0 coordinates. So that's pretty handy. That's good news. I was really hoping that this 0 wasn't going to show up here, and then what we would do instead then is say like, aha, well, we do need to still report counts of 0 and make sure that they appear. And what I thought I would do, which would be clever, would be to start the sum at at 1, essentially. Let's say do a count and then do a map where we take the chords, comma, count to chords, count minus 1. So this is something that should ensure that we see zeros, even if zeros were suppressed correctly. And okay, we're reporting a sum which is 1 higher, just because we don't really want to see that. And then subtracting a 1 from it afterwards. So this will make sure that we see zeros, even if there's no actual data nearby to trigger that. So I'm just going to reformat these things just a little bit. Cool. And if we turn this back down a little bit, we should see a count of 0 again, though for a different reason, because we actually wanted started at 1, counted up, got a 1, and then subtracted 1 from it. But let's think now. So we have just a nice little fragment here, right? That's meant to go and tell us about the number of mines adjacent to a particular location. We could write that unfolding code now if we wanted to. I'm just gonna try and see what happens. So let's not call this neighbors, let's call it like reports. Guesses dot iterate. And what we're gonna do is, what's the right way to structure this? Because the thing we want to go around the loop are sort of more guesses, but the thing we want to come out of the loop are guesses and their counts. And it's not a great scene to sort of send in a count of 0, because that might not be the right count, and it will cause immediate unfolding. So what to do here, what to do? We have different inputs and outputs, different types of inputs and outputs, which is sort of bad for a fixed point iteration. Let's just, I think we'll end up just copy and pasting this code. This feels a little silly, but let's start with our guesses, and we're going to iterate with so what iterate does is it starts from a collection, initial collection, and repeatedly goes, oh, that's what we can do. We can totally just start from an empty collection and then write the logic to fold in our guesses each time around. And okay, let's just do it this way for the moment. So this is going to be a set of x, y locations that are our current guesses. And we're going to take these. We're going to take these with our complicated bit of logic here. We're going to take our things, do some current guessing, and call this counts. And our plan now for iteration is we should just stop if for anything that's not equal to 0, like just that's not a good reason to keep guessing. But if something's 0, we should just guess all of its neighbors. I wonder if maybe I should just write a little bit of logic here that oh, we're doing something silly. I guess we're looking at like whether there's the 0, 0 case is still applied here. We could write a little bit of logic that just enumerates all of the neighbors of a thing. Should we write that? Let's try that. Simple iterator. And we will do, I guess -1, 0, 1 dot flat map. Bear with me for just a moment. I think that's roughly right. Oh, we don't do impl of. Yeah, okay. Sorry, I haven't written these sorts of things in a while. Do dot into iter. And I think, unfortunately, I think into-iter returns references to integers here as opposed to actual integers, because Rust is still working on that. But if we do this might work better. Try to format this a little bit more, well, less horizontally. Yeah, that's good enough for me. So neighbor should now return an iterator over various things, and we could say, I guess we call the XP and YP. All right, it's much shorter, much shorter now. So, sorry, we did this so that we can now write a little bit of code here, which is just take the counts. We're going to keep the counts, chords. We'll look at their chords and count. The count is 0. And then we're going to, what are we going to do to that? We're going to flat map that, taking the chords, which are exciting to us, and not the count, which is no longer exciting. And we're going to, I think, just enumerate all the neighbors, right? X, Y. Sorry for bouncing around there. So what this is going to do, this is sort of important here. This is we left the 0, 0 case in here, which means that anything in counts that we've already sort of evaluated will also go around again. But I think what this does, what this means to do at least, is take the current set of guesses. We're going to go and find the counts for each of these current set of guesses, do the appropriate sort of +1, -1 trick here. Keep everyone that's exactly at 0, or and we do have to be careful here, right? We have to be careful because we want to make sure that we concat in the counts themselves, like current itself. Let's just do that explicitly. We'll make this a bit more clever in just a moment. Now, iterate is frustrated for some reason. This looks like that's because we just need to use, well, the first worry is that. And I suppose we need distinct also. Sorry, distinct is is that not right? Where does distinct live? Oh, these are tests. I want tests. Differential Dataflow source, operators, yeah, reduce. Why are you being so complicated here? Yeah. Threshold is the trait that has the distinct method in it. All right. Great. Can't compare references to, yeah, that makes sense. All right, so we have reports coming out of here. It looks like Rust is currently okay with this iteration fragment here. Now, what we haven't done is report any of the counts. Let's just not do that yet. Let's just announce whatever we unfolded to, and need to do a little bit of thinking here to make sure that we don't accidentally go unbounded, right? So, well, let's just see what happens. That's fine. Unused variables. Oh yeah, okay. So that's an important bug there, yeah. That we need to actually go and add our arguments to these things. That wouldn't, it would reach fixed point pretty quickly, I suppose. But consolidate isn't used. Yeah, this is Rust folks telling us that they're planning on changing this in the near future. All right, so I suppose I should put consolidate back in. So something exciting has definitely happened here. Well, sorry, I say definitely. That's not necessarily the case. We have a bunch of locations. I thought these were counts and stuff, but these are actually just coordinates. So we started at 0 and we spilled out in a bunch of different directions, and it did in fact wind down at some point. I wish I could. If I were more clever, I would have figured out how to draw a nice little picture of this. We could try to do that. I don't know a great way to do that, actually. It's mostly negative 20 up to positive 20. And vertically, what, 14s, 13s? I'm trying to think if we can draw like a little bitmap and just sort of blat it out to the screen of where these things ended up. I'm not sure I want to try that just right now. But what these are telling us is that other than at the perimeter, maybe what we could do. Let's grab the these counts again, essentially this fragment here, and reports.consolidate, and all this jazz again. And I'm just going to report the non-zero things. So we're not going to see the empty spot in the center. So let's take non-empty dot filter. Actually, sorry. No, this will be fine. Yeah, good. Sorry. And we're going to keep the things where count is bigger than 0. Use a reference to 0 because I want to screw this up. X and Y are indeed intentionally not used. All right. So we're seeing now a lot of 1s. I don't have a great read on whether, to be honest, it seems not too dissimilar in size, actually. I wonder if that's, I mean, it's possible that we sort of snaked around all over the place. And, oh geez, let's is there, what's a good way to grab all these results and just sort of blat them down into the screen? We can definitely fill out a nice little array of something. The cursive thing I have actually is like a not insane way to think about doing this, but I'm not brave enough to wire these things up together right at the moment. So instead, let's so Timely Dataflow has some handy things for capturing data. Let's actually find fun extract. So extract is a thing that is, if we go and we capture into, a bunch of Timely's tests use this essentially. They point themselves at a stream, capture all the events from it, it puts them in a canonical representation, and you can then, like, it's now outside in your hot little hands in your program, and you can just go and use this. So we need to put things into an MPSC receiver, which I think is just capture into is a good example of that. Receiver, not sender, is that right? Get my head around. Oh, we have an example. Hooray! All right, let's double check the example here. So we capture. Yes, I see. Sorry, we capture into send, and then the receive side implements extract, which is right. Okay, that makes a lot more sense actually. So let's do this over here. So outside of all this timely computation, we're going to do. I have no idea if this did sync. Okay, cool. Channel, yeah. No, you don't like that? PSC. Well, we'll sort that out, I suppose, in a little bit. We'll wrap up a handy little. It is also not in sync, I think. Oh, it's probably just angry they can't figure out the type yet. That's fine. So we'll probe here and we'll do a capture into the, how do we structure it over here? Make a little clone of it in each of the workers. So what we're doing now is handing out a copy. This is MPSC is multiple producer, single consumer. And we are going to have each of the workers, not in there, sorry. Each of the workers is going to make a local copy of the send side of the channel. So they're going to grab happy little sender. Here they're going to do all their data flow stuff, and we're going to capture into send, I hope. That's what it looks like, yeah. Cool. And we need to use some timely traits. Capture into. Let's see. Capture. All right. Timely data flow operators capture. Great. Is that not capture into? Well, in just a moment. Oh, yeah, right. Sorry. So we need to do dot inner. You can't capture a differential data flow collection. You can only capture the timely data flow stream that's inside it. And now outside of our timely data flow computation, let's grab, essentially do this, let extracted equals recv.extract. And do we need to, no, we don't need to join or anything like that. And what does extract produce? We apparently, yeah, vec, great. So it's going to give us a list by times of all of the records that were in there, and I believe, yeah, D and D are ordered, so it's going to sort them for us, so they're in some nice canonical representation. No method named extract. What we probably need to use. Extract, and now if we walk through extract, hopefully what we see are exactly the same contents that are in here. And what we can do with this, I propose, is let's let to print. We're gonna make it a big vec of vecs. I'm gonna make it 50 wide, and I don't remember how tall it had it to be. Let's say 30. Where we were going to put zeros in there, and zeros. Now let's put x. What's space? Great. We'll put nothing in most locations. Then we're going to walk through all of our counts, and we're going to add in stuff for the counts. So we're going to need to do time, comma list, because although there's just one time, the 0th time, we're going to need to actually name it and make sure we acknowledge it. In extracted for, and now, okay, the things that we have in our list here are now this sort of crazy mayhem. So we don't really care about everything, anything except the first few fields, but that's fine. So we're going to go and take x and y, and my plan is to do print of, now the other thing is 50, I'm going to say we do 25 plus x, 15 plus y, gets to be equal to that. And we'll have to do a little bit of lying here, I think, to make all these types work out. And I'm trying to remember the right way to fake out this stuff. Super frustrating. Only U8 can be cast as car. Well, screw you. What? Why is it a U8 at all? Actually? Oh, because because diffs go up and down. My memory for all this horror is Rust is a little too good at making my life complicated. Let me just steal for a moment from the handy Sudoku project how I did this over there. Yeah, advanced complicated data flow shit, and like, so we just used U8s everywhere. That's super not satisfying. My word. Well, this is being held up here in the moment by Rust being helpful. let's so to print needs to be mutable, easy problems to fix. So my plan is to now just sort of barge through this thing, and x goes up, y goes down, so we're going to do line after line. Fortunately, the array is the wrong way around for me just to iterate through it pleasantly. Print doop-a-doo-doo. Sorry, what's going on there? It's crazy. All right, and we'll have to. We need to move. Sorry, was our mouse. We have to move our mutex wrapped thing into the closure, so the closure will own it. And cool. So this is the shape that we discovered. Curiously, oh no, sorry. Like yeah, we did that filtering to only keep the positive things here. It is why we're seeing empty spaces instead of like a solid mass of X. But this is, starting from our, I'm guessing roughly there, our 0, 0 guess, what we expanded out to. And you can see some of the classical Minesweeper shapes like this. And there's almost certainly a 1. This is almost certainly a 1, also even without seeing what the numbers are. You know, 1 there and a 1 there. And yeah, and if I were just a little bit smarter, I'd be able to print the numbers there. But you know, my day-to-day life, unfortunately at the moment, is doing crazy join optimizations and stuff like that, rather than figuring out how to safely convert signed integers to unsigned integers. What happens if we go through, sorry, Rust famously, oh no, sorry, famously helpful error messages. Yeah, I know, I can't. Oh. Okay, this is deeply upsetting. All right, so we're going to do something slightly different here. We are going to have these be all zeros. Does this actually work? So hoping to do this cunning little manipulation down here, where we can't add. Oh, I just ridiculous. I give up. I'll sort this out offline and try to figure out the right way to actually print numbers to the screen, which is not something that Rust excels at. All right, so I'm going to stop for the moment, mostly just because I'm frustrated now and not making progress. Though I will throw this back up because it looked sort of neat. And you can all see that we're obviously well on our way to doing incremental evaluation of Minesweeper regions. Ideally, in the future, ones that don't expand quite so much with absolutely no work. But this happened to be around 0, 0, but we could have made it out 4 billion or larger x and y values, which means that we could have multiple of these evolving sort of simultaneously in principle, and as we go and sort of change some of our guesses around, which will be much more interesting, I hope, once we actually got some numbers showing up here. But yeah, let's stop for the moment. I'll just sort of ship this in a more manageable bite size, and I'll sort out how to do some of these pretty display of information-y type things, and we can reconvene. All right, thanks very much.